seminar, or can I say this? Right? Okay, so I will start with the definition of non-expanding horizon, which is not very important here. However, I really like it, so I want to show you.
Yeah, because now we touched a moment. For now? Yeah.
Okay, so non-expanding horizon is n plus now the dimension convention. So space-time will be n plus 2 dimensional. So if you want to refer what we're talking about space-time, think of n2 dimensional. But this is an abstract notion, so it's not necessarily embedded in space. N plus 1 dimensional manifold, and there is symmetric tensor on it of signature 0 plus 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 plus, and there is torsion-free covariant derivative on the tangent bundle, and this derivative is metric. And now the statement is that if this is true, then actually every and then the vectors which are degenerate, which point in the degenerate direction, we call null. It makes sense because they are really null with respect to this symmetric tensor, and it turns out that every that for every symmetric tensor the following is true. And the meaning of this, if you want to use terminology from general relativity, is that this null surface is divergence free and shear. So the shear and divergence of the vector L is 0. And it's sort of surprising whenever I show this funny result, that people tell me, "Oh, you are mistaken. This is actually assumption. This is not." And even yesterday, when I was giving this talk, Piotr Kruszka also said, "Oh, this is assumption." But no, it's not assumption. Actually, it's really already follows from this, which is a bit intuitionally not good. Okay, so this is a shear-free non-expanding surface which can have its own intrinsic definition. And now, so long time ago, we asked ourselves with my PhD student Tomek Pawłowski. No, I was so stupid that I gave reference, but I didn't give author. I didn't give authors of papers, and actually I'm the author. And Tomasz Pawłowski, it shows even more stupidity. So we asked the following question: upon what geometric conditions this surface becomes curved horizon? Or upon what conditions it becomes even extremal curved horizon? And then we found those conditions, and the answer was that there are some equations which make this geometry and some symmetry assumptions. And this is what this story is about. So let me start from the beginning. So this is this non-expanding horizon, and we can see what ingredients has geometry. So given this geometry here, we can define rotation one from potential, which is given by this equation. So since this derivative preserves the degenerate direction, the derivative of null vector will be again proportional to null vector. So that's why this omega is really well defined. This omega depends on choice of L. And another degree of freedom is transversal expansion shear, which is just a name. So if we introduce a function v, which satisfies, to make things easier, this property, and consider slice v equal constant, then we can introduce this tensor, and this tensor is another degree of freedom. It contains information about the covariant derivative. from omega we can read what is surface gravity, which is this. So we end up constructing for data that on every slice we have induced metric tensor, which doesn't involve V because it is constant. Then we have omega, which a priori is not constant, and S, which a priori is not constant. Now, if we consider, now we embed this surface, space-time. And if we now consider embedded surface, as I mentioned, we embedded in n plus 2-dimensional space-time. Then, after embedding, we find the following relation. So this is the surface gravity defined intrinsically. This is the derivative of this rotation one form also defined intrinsically, but this is the space-time Ricci tensor. So this information comes from the embedding. And now if we assume Einstein equations, and if we assume very general with T mu nu, however, if we assume positivity conditions satisfied by T mu nu, then it turns out that this is zero. So this equals to this. And now we can actually even construct, now we can choose L such that K is constant and then omega will be dragged by L. This is what we usually do. And then we obtain the following evolution equation for S. So derivative of this S induced on a slice is minus kappa times S plus this thing. And here we have again a contribution from, so one can view this equation as equation which relates Ricci tensor in n plus 2 dimensions with Ricci tensor of this n-dimensional codimension 2 slice and some extra stuff. Usually this happens to be related. And now generically, this equation just gives us evolution of this S. However, if we insist that there is a killing vector, so actually S is constant, so this is zero. And if we insist that this killing vector is extremal, meaning that the surface gravity is zero, this term is zero, then this simple evolution equation turns into a constraint on omega and on this metric. Two. So this is exactly the scenario which we are assuming. So we are assuming that this after embedding this there is in space-time. So to make things simpler, we could just assume that there is a killing vector and that there is a killing horizon. If you want to be a little more precise, then actually it doesn't have to be killing horizon. It's enough that it satisfies this equation and this equation. So I call it killing horizon first order. Then notice we have the zeroth law of thermodynamics, which tells us that surface gravity is constant along all the surface. And if we assume that this constant is, zero, if we assume that this constant is zero, then we obtain the following equation, which is satisfied on every slice. So these are this is the covariant derivative, and means that this covariant derivative with respect to this induced metric tensor. So it's not space-time derivative, it's just this derivative of this codimension 2 surface. So this is derivative of this omega, also defined here, plus omega minus the 1/2 Ricci of this metric plus a space-time Ricci tensor, which is subject to Einstein equation. So for instance, we can put here 0, or we can put here lambda times JB, or if there are some other matter fields, then we can put here the stress energy, the momentum energy tensor, but in that case, we also have matter fields, so we have to use we have to also write equations that matter fields satisfy, which are evolving around this line. This is also the case we could consider. Okay, and so what we consider in this talk today is when we assume vacuum Einstein equations with some cosmological constant value. So this is the equation. So let me now extract. Forget everything what I said and you didn't understand. We end up considering. Well, I'm sorry for this 2. This 2 should not be 2, it should be n. We construct n-dimensional compact manifold, and also there will be a certain evolution of notation for this manifold. On this slide it is denoted by C, on next slide it will be denoted by calligraphic S. So we have a compact manifold, which also is not necessarily compact. Whenever it's compact, I will say it is compact. If it's not compact, then it's also possible. And those with the metric tensor and the one form for single this is vector. Lambda is a constant, and this is this beautiful equation which they satisfy. And now, important information for you, what we can do with this equation. So suppose that you solve this equation and you come and give me omega and g which satisfies this equation and ask me what you can do with the solution. Then I can construct for you a exact solution to Einstein equations. Namely, I will take my surface C, for some reasons I will denote it by S now. I will multiply by extra 2 dimensions, and then using this omega and g, I will define the following metric tensor. So for S, it will be the same metric tensor as it was, this is defined. However, from the extra 2 dimensions, du and dv, we consider such null element with components given by omega and also by variables v. So here explicitly we see variable v shows up. The variable u doesn't show up at all. And now what is funny is that this metric tensor satisfies the vacuum Einstein equation with n plus 2 dimensions. And by the way, this tensor SAT, which I defined previously, is 0 for this metric tensor. So now you can see that since u doesn't show up here at all, then ddu is a Killing vector. The extremal horizon which we started with is v equal to 0 surface. So then on this v equals 0 surface, the vector field ddu is this killing vector that makes this vector field. That's horizon killing for us. However, now you can notice that there is also another killing vector, that there is dilation here. So if you remember Wheeler's wedge, or if you remember the formula for a killing vector for Schwarzschild, but in some Kruskal coordinates, then those killing vectors usually have this form, like this. So, and notice that this K is also, and now.
Why you call it dilation? Dilation is with plus.
No, this is the.
But you cannot change this. Saying u minus u.
Well, this is dilation. It's just.
No, it's mu.
Okay, so
direct space.
it's minus dilation.
No, x u du t dt plus r dr plus, not minus, and you cannot change this.
Okay, but okay. I agree. I call it dilation just when I restrict it on horizon. And then on horizon V is 0. And then it becomes.
That's okay.
Just good view.
Yeah, but in space time.
Okay, thank you. Yes, so I consider it dilation of horizon. But now, can you see that K is also a killing vector of this method? No. It's not easy, trivial. However, notice what this K generates. It generates symmetry that rescales V by a constant and divides U by the same constant. Okay, and now let us see what happens with this term. Here we rescale V by constant, divide U by constant, they cancel. Okay. Now, if we take this term times du, the same story, which we scale V by constant, divide U by the same constant. Well, here we have this squared, so we can think that it's not working anymore, but we have also du, so the square du squared. So you can see that indeed the transformations generated by K really are isometries of this metric. So constructing this metric, we gained one more killing vector.
Is the Kerr metric included in this class?
Yeah, the extremal Kerr metric.
Extremal.
No, sorry, it's not. No. This is
Here, horizon change.
this is some limit metric which can be obtained from extremal Kerr by certain limit of coordinates which changes the metric test.
Yeah.
But this is like cylinder. It's asymptotically, it's not asymptotically, it's Kunstglas. Yeah, that's very good. Good, yeah, this is Kunstglas. Right. So those surfaces U equal constant are null surfaces. They are emanating from this horizon, and each of them is also killing horizon. So each of them is divergence free and shear free. So this is space-time foliated by divergence free, shear free. Okay, and now going back to this equation, there is one more application of this equation. Namely, if we consider space-time that is foliated by non-expanding shear-free surfaces, then every non-expanding shear-free surface is my non-expanding horizon. So there is also omega defined on that surface. And in that case, that omega will satisfy this equation. And let me recall you the previous equation. The previous equation was like this. This is like this. So the only difference is this transformation from omega to minus omega. So it means that mathematically the same equation applies to a different kind of surface, which is still partially a mystery for me. Why the same equation applies to different surfaces. So, for instance, if you solve this, but actually the metric which I wrote here is exactly the metric of the type which is on next slide, but next slide is yet more general. And this is the Kunstglas, exactly the Kunstglas metric, pretty general Kunstglas metric has such foliation, and on each leaf of foliation, this equation is satisfied. Okay, so now let us go back to this equation. Let us consider four-dimensional case. So in 4 dimensions, we have two-dimensional Riemann surface and metric tensor and the one form, and this equation, which in 2 dimensions, this Ricci becomes just a function times metric tensor. So this is our equation now, and now we can do this first kind of analysis of what is possible, what is not possible, what is excluded. Actually, this was due to Jacek. Yes, he pointed out that we can do it. So when we contract those indices and integrate along sphere, along the surface, then this term drops, other term is positive, definite. Integral of k is given by Gauss-Bonnet, it gives topological invariant. So at the end of the day, we obtain equation which here has topological invariant of manifold. This is two manifold. This is area. This is something positive plus lambda. So it gives us this inequality. So we can now analyze for what values of lambda and what values of genus there exists possibly solution. So if genus is 0, meaning sphere, all lambdas are allowed. However, if genus is bigger than 1, then only negative lambdas are allowed. If genus is 1, meaning torus, then either lambda may be either arbitrarily negative or it may be 0. But if it is 0, then if we go back to this equation, we can see that we have 0 here, we have 0 here, which means that omega is also 0. So then we have quite trivial solution. So this is this first kind of analysis tells us what we can expect. But it turns out that we can do better. So okay, so let me see, maybe I can so let us start with this case. Okay, let me start with I wanted to maybe change the order. Okay, so what we did first with Tomek Pawłowski is we considered sphere, we assumed axial symmetry, and then we wrote this equation. In case of axial symmetry, this equation becomes just ordinary differential equation along what is the word, meridian of this sphere. We integrated, we eliminated possible singularities in the poles, and we found that the only solutions, well, we consider lambda equals 0 case. The only solutions are those defined by extremal curve. Next, we added Maxwell field, and then again we obtained that the only solutions are extremal horizons of Kerr-Newman. Later, with Eric Book, we considered the case with lambda, but also this case was in the meantime considered by Kunduri and Sirki, who actually even wrote living reviews on all this subject. And a lot of generalizations of this result was derived in higher dimensions. So, or for other matter fields, people considered Einsteinian fields instead of Einstein-Maxwell. People considered higher dimensions. And there are many generalizations to higher dimensions. Okay, so, however, this result, which we have here, can be understood as a sort of uniqueness of scale. That if you want to have axisymmetric extremal horizon of sphere, there is it has to be the curved horizon. So this equation forces horizon to be curved horizon, and in this way it somehow explains why the curve metric looks as it looks. So it is heuristic. Then Crucial and Real ask the following question. They ask, what if we consider this equation? However, if we assume that rotation of this one form omega is 0, that means that black hole is not rotating, or this is abstract black hole. Its horizon is not rotating. And then they found that the only solutions are omega equals 0 and k equal constant equal to lambda. So actually, there was something funny. I had a proof of this theorem in my earlier paper with Ashtekar. However, I gave a proof, but I didn't realize that this proof proves that theorem. So, I just had a proof, but I didn't conclusion. So it doesn't count. However, The idea of this proof is that you do some integrals and again you get either topological invariants or positive things which are positive definite. And in that paper, Crucial, even though he is a very exact person, but I think he wrote with some other he wrote it with Harvey Rio and Paul Todd, so probably the other calculus were not so exact. At first, they delivered the proof in 2 dimensions, it's arbitrary cosmological constant, and then they made a lot of footnotes like that. Actually, the same proof goes through in any dimension, and actually, this is the same proof. So finally, they claimed that they proved it in any dimension. However, later, people found counter examples in higher dimensions. So at the end of the day, the conclusion is that as long as lambda is bigger, sharply bigger than 0, then this conclusion is also true in all dimensions. However, if lambda is less than 0, then there is some other case when people here found, and they also worked, those people worked out that case. So they have now another example of non-rotating extremal horizons. Okay, so as you see, we try to solve this equation somehow by making some simplifying assumptions. First, we assume that axial symmetry in sphere. Now we assume non-rotating case. So now the next assumption, simplifying the assumption, we try to. Yes.
So it's not okay to classify or something like that.
Yeah, this is what according to the safety, this example is the only one. However, I'm not sure. Yeah, this is something we will have also checking in the literature and making sure. Okay, so another simplifying assumption which we tried was, let us consider this equation on a surface which has higher genus, and we're even so sophisticated that we use Euler characteristics instead of higher genus, but it seems that everything works even in this case. So we found that again, if we consider this equation on surface with higher genus, then omega is 0 and k is equal to lambda. So, and actually this, if you knew history of black hole theory, then you would recognize that this theorem is an analog of Hawking first theorem, which was that the black hole horizon should be topologically a 2-dimensional sphere rather than anything else, or a bundle of spheres. And so this is different. This is a different argument. This argument was that you could consider outer holes non-trapping or marginally trapped surface, then you can hopefully prove that the surface has topology of S2. Our argument doesn't use global properties. We only use equation, Haber-Bosch equation. However, conclusion is similar. Because what does it mean? It means that at least if we want to consider rotating black hole, then the only possibility is that it has spherical slices. Well, except for this quite very simple case, when omega is 0 and k is lambda. Okay, but by the way, do you know in what kind of metric this? And notice that in this case, since this is Euler class is less than 0, this k is negative, so it means lambda is also negative. So both k is negative and lambda is negative. So do you know in what spacetime it can be embedded in what class of spacetimes? There are those spacetimes which you can construct in the following way: that you take Schwarzschild metric, but in Schwarzschild metric we have 1 minus something, so you replace 1 by minus. And then at the end of Schwarzschild metric, there is metric of two-dimensional sphere. So you replace metric of two-dimensional sphere by metric of surface of metric of surface of curvature. Okay. Actually, in that case of curvature, just -1. And the last thing is to make sure that this is extremal case, you have to adjust the mass term properly. But then this polynomial which you obtain, this quadratic polynomial, it does have roots if lambda is negative. So indeed you obtain extremal space time. So you can put either torus there, or you can put surface with negative constant. So in this way we obtain a counterpart of Schwarzschild space-time. So this works not only for extremal case, it works for non-extremal cases, but among them there is. Okay, so step by step we eliminate some cases which we show are a little simpler, but still let me tell you how we prove this. So actually for this, we turned the rotation of omega into a pseudoscalar of capital Omega. Then the most difficult part, I would say, was showing that this is not vanishing. And here Wojtek Kamiński showed his skills in complex geometry. And I'm not sure that I even now would be able to repeat from the top of my head those arguments proving that indeed. So it either never vanishes or vanishes everywhere. This is the statement. And then we derive, so given equation, what we do is the following. You keep integrating this equation and you obtain new equation, basically. So we obtained first integrability condition, and then we obtained second integrability condition. And notice that here we have only n bar, which means this is a complex equation. So complex, we define the complex value function and obtain some complex equation, and here we obtain another. So this is like holomorphic, sort of holomorphic derivative, and this is second holomorphic derivative. And then we noticed that actually it was again Wojtek who noticed this, that the second integrability, sorry, let me remark from the second integrability condition implies that there exists a holomorphic vector field globally defined on our two-dimensional surface. But what is holomorphic vector? Holomorphic vector is a vector that defines a global group of holomorphic transformations. And we know that for higher genus, such set of such transformations is limited, or there are no transformations like this. So in case of genus bigger than 1, it just means that this vector is 0, meaning that this is constant. And for torus, there were some solutions, so we can just by hand check them and solve them. However, the conclusion was that indeed the only solutions are omega equals 0 and k equals S. I think we also used Khrushchev's and Tol's and Rios paper for one specific case when k equals lambda divided by 2. This is what we're not able to prove without this. Okay, so now we go back to sphere. So now we learned that the only interesting case is sphere, and it's also physically sort of interesting. Well, we know from Hawking that this horizon is connected with the sphere. So let's go back to sphere. And now Paul Todd conjectured in 2005 that actually the assumption of spherical symmetry is not necessary, that maybe every solution has axial symmetry. And I remember spent all September, there was a workshop in Newton's Institute in Cambridge, and Paul taught with Crucial and some other people, maybe Maciej Lewandowski, they were thinking how to prove it, but they were not able to prove this. Okay, so what they did was something else. If you cannot prove difficult theorem, then you try to calculate something. So they considered the extremality equation, and then they considered linearization of variation of this equation and linearized variation in neighborhood of G and omega given by extremal curve. And then they showed that actually there are no new solutions, that every variation every solution they find is again curve, extremal curve, linearized extremal curve. So, or it's enough to show, given what we know, that it's axisymmetric. So in this way, they showed that at least from linearized argument, you don't see any other solutions. And now in 2023, two brave knights, Dunajski and Lucietti.
Maybe I should comment.
Yes, the previous. Yeah, I think you also had some.
The point was the following: that suppose we have this background extremal curve, and we perform linear perturbation, which is no longer symmetric. This is the idea.
Yeah.
And then we prove that there are no non-trivial solutions. And in fact, the starting point was my paper with my student.
I see.
And we have proved almost everything up to, so you have a space of perturbations which is infinite dimensional Hilbert space, and up to, I don't remember, 16-dimensional space of lower Fourier transform. Because you see, when you have
yes, every solution.
axial symmetry of the background, you have Fourier transform.
Right, so every solution
So each
labeled by
so each magnetic, let's say, perturbation which is higher is 0. However, there exists low space which should be somehow done on the computer because this analytic inequalities does not work.
Okay.
And this was the gap which was solved by Krushkel cut off.
I see.
But the idea was smart, not that Krushkel cut off.
Okay, sorry, I should remember this. So you guys reduce this problem to finitely many boxes
To finite dimensional system.
of magnetic number, which you were not able, but still it was matter of.
And there was the
Okay, yeah, so indeed they use computers, and then finally they found. Okay, but still it was only. Did they also do something non-linear in paper? Or
Pardon?
did they also have any non-linear result in their
No, the main problem was that the linearization, so not far away from the curve we are sure that there are no non-zero solutions. But maybe far away, there is another island of matrix where there is another solution. And I thought that this problem was not solved in the nice suicide argument, which was different.
Right. Okay.
They must have shown that there should be only two zeros on
I think
so it was
that was that was this original Paul argument. Which in which he showed that omega gets to 0, so it looks like two poles of axial symmetry. Yeah, that's true. Okay, so now those two heroes come, and now maybe we can even learn something from this, because they actually, so it shows that if you have a good education, then actually you can do a little more than people who don't have education. I will tell you now where this education is comes into the game. So namely, so what they did was the following. They checked that in the cases which we know, when there is axial symmetry, then the relation between axial symmetry and omega is the following: that there exists a function which actually is explicitly in that case given, such that this vector d upon d phi with lowered index is given by this relation. And they also knew one more result due to Anderson, Mars, and Simon, which comes with the name MOTS. Marginally trapped outermost surfaces, and there is MOTS operator, and this is actually, and if you impose this condition, then actually this becomes MOTS operator, and then they just knew from those guys, from Anderson, Mars, and Simon, that on a compact manifold, that given omega and g on a compact manifold, this equation has a solution, and actually that solution to this equation is a nowhere vanishing function. So you can see, if you write this equation, if you eliminate this Poisson bracket, then you have Laplacian plus some sort of linear term, some not self-adjoint term, but you don't worry, and you have also divergence, and everything is acting on zero. So actually, to make things funnier, I also, a long time ago, before those guys, I introduced this operator. However, I was never able to show anything about the existence of solutions to such equation. So I only ended up concluding that well, if such operator, if omega is very small, then probably the spectrum of this operator is not much different than the spectrum of Laplace. That was the only conclusion. But those guys, they were serious people, and they really showed that there exists f, and that this f is nowhere zero. So, and knowing this, they postulated the following. They postulated, let us prove actually that the vector field, this unique vector field due to this theorem, given by this condition and by this definition, that actually is a Killing vector. And how is a Killing symmetry of this data? How to show that something is a Killing symmetry? Well, the square of this has to be zero, so just calculate the square of this. And when they did this calculation, and when they used this equation, they showed after that many cancellations takes place, and that actually this square is just a pure divergence. So if you integrate this along a compact surface, then you obtain zero. So it means that the integrand is zero because it's positive. So in this way, actually this works for arbitrary dimension. This part of the theorem. Now the second part, so this is the first part, that there is a Killing vector from G. Now the second part is whether this Killing vector kills omega. And then, if you apply this, then you find that actually if value of cosmological constant is negative or zero, then you can prove also that it is true. But if it is, but otherwise it is positive, then you cannot prove it. Then you don't know whether it is true or not. However, in 2 dimensions, there exists and in 2 dimensions there exists additional argument, and then actually this is true for arbitrary lambda. And here in this proof, they even used one of our identities, which I showed on the previous transparencies. So at the end of the day, the unknown case is when okay, so what is unknown? First, we don't have proof for. So in 4 dimensions, now so let's start with 4-dimensional space-time. Then we don't know what about coupling of, say, Maxwell fields. And if it's possible that if we couple Maxwell fields, then still this theorem is true. However, this proof, as it is, it doesn't work. One would have to work on it and see why. And other cases is where R when lambda is bigger than 0 and dimension is bigger than 2, then again we don't know. Perhaps this theorem can be generalized or perhaps not. But this is really, really beautiful result, and in view of this review of the previous results, you can see how not trivial it was to derive.
Jurek, I have a question. If you don't assume that this divergence vanishes,
Right.
and you write such a psi with any f,
Yeah.
can you say something about
Yes.
field as a conformal field, not just a Killing? So
Okay.
so take a conformal operator on this
Okay.
right hand
Okay.
side.
Yes. So if you don't assume this and do the same calculation, then you obtain, in addition to this, you obtain a term plus divergence of psi times some expression, local expression in the topology. So this plus this.
Yeah, but if you put this on the left hand side as the square of this divergence, maybe this conformal operator, the square of conformal operator, is also a total divergence.
I see. So
Okay,
I see.
I'm going to change this argument.
I understand. So instead of this, you would write plus function by
You remove the trace of this symmetric part of psi.
okay.
And you take this square, and what happens in this calculation?
But wait, should we move?
No, instead of staying, because here what you do, you take a symmetric.
So you mean you relax
You take a tensor which is symmetrized part of the covariant derivative of psi, and you remove -1/2 divergence. This is conformal, okay? And you take a square of this conformal. And what happens on the right hand side?
I see. So instead of describing this, you would here take minus this
-1/2 divergence, C times the level.
Okay, it's interesting.
It would be interesting to us to check what is going on and something.
Yeah. I agree.
You understand?
Yes.
Jurek, I will ask, what is obtained? What is the result?
The result is that this is 0. So
That is that is so
I is a killing vector of G.
Okay.
But the equation star means that you have everywhere symmetry.
And big result is that every solution to this equation has G has a killing vector for this solution, and omega is actually annihilated by this killing vector, but that happens only if we restrict the dimension or values of lambda.
And to get Kera's only solution, what else do we?
Because this symmetry is successful.
Okay, so this already implies that Kerr uniqueness. So in case of for Kerr uniqueness, n is equal to 2, lambda is equal to 0, or we can take lambda not 0, and if we consider this equation on sphere, then we see that it has to be axisymmetric, and then we have already solutions, and we know that for axisymmetric, Kerr the seater or Kerr the seater is the only possibility. And if we wanted a different surface than sphere, then we have our previous results showing that then there are those only trivial solutions. Okay, so this is a big result, but let me also give you some newer results, which are not even not published yet. So one result is local intrinsic rigidity of non-rotating, correct? So if we are still in 2 dimensions, and if we assume it is non-rotating, however k is never 0, then we can go back to this integrability condition which I wrote here. And now omega is 0 in this condition. So let me show you what happens when omega is 0. So if so now if omega is not 0, then this is a complex valued function. This is complex valued operation. However, if omega is 0, this function is real valued. So we can also take complex conjugate. So in case when omega is 0, we have actually 2 equations. We have m bar A, m bar B, nabla A, nabla B, k minus lambda divided by 3 minus equals 0. However, we also have the complex conjugate, MA, NB, nabla A, nabla B, k minus lambda divided by 2 minus 1 equals 0. In this case, we studied with Adam Szyszewski, and we showed that if the 2 equations simultaneously are satisfied, then there exists a killing vector of this metric, and in this case, this can be also checked that this killing vector will annihilate omega. So it means that at least for if k, unless k is constant. So for non-constant k and non-rotating, we have a local result. We don't refer here to Adam. In our theorem of this rigidity, we didn't use compartments, right? We only commuted equations and we obtained. So
this assumption omega is equal to 0, what is the meaning of this?
well, it is
Capital omega, capital omega.
this is the same as it follows from this. Because the omega is omega times area. So okay, so in this way we have a local existence of symmetry. However, this works only for 2 dimensions and only for non-rotating case. And there is one more new result which we also have, namely when we no, don't be looking. Now, when we prove this uniqueness of the axis symmetric solution on sphere, what we do is we choose only those solutions that are not singular on poles. But now we can admit also some singularity, namely we can admit conical singularity, which means that for every pole there is a constant such that if I rescale the 5 coordinate by this constant, then actually I remove the singularity. However, this constant is different on one pole and different on another pole, so I cannot do it for 2 poles simultaneously. And Eric investigated such solutions, and he found the following. He found that actually those solutions of this equation, they have that such singularity. However, omega is not singular. So now look what we do. So what can we do with 2-dimensional metric defined on sphere that has unremovable conical singularity? This is question. what we can do with this. So we can do the following. We can consider the solution on sphere without one pole times extra circle and introduce one more coordinate. And we can also consider this solution on another S2 with removed the previous pole, the other pole times S1 and coordinates. And now we can write the metric like this, where coordinate. Okay, so we are given a metric. Let me start with this. We are given this two-dimensional matrix. And now what is wrong? If f at 0 equals 1 and f at p equals 1, then there is no conical singularity. However, if f is not 1 and 0, we can always divide this phi by f, and we define and change the range of angle in this way. However, if f of phi is different than f of phi, then we remove singularity in one pole, not in two poles. However, we can do the following. We can define metric like this, and this metric is well defined on this three-dimensional space. Then we can do the same in the second pole, and this metric is well defined this, and then we have a gluing map, which will glue this with this. And at the end of the day, we obtain a smooth tensor, which is symmetric, which is of rank, which is that degenerate metric because it has a degenerate direction, and it exactly defines for us three-dimensional horizon. And this horizon, it has the Hopf vibration structure. So this vector DDV generates the action of group U1, which you can identify, and you can see it makes it. So this becomes three-dimensional topology of the three-dimensional sphere. This is the one action of U1, and if you consider this vector, it defines another action of U1. And omega has no singularities, so omega is just well defined both here, and it's smoothly is good. So in this way, it shows that we shouldn't throw away those solutions which have conical singularity. We can construct from them a smooth horizon. However, this horizon doesn't have global section. This horizon has topology of S3. And are such horizons in nature? So if by nature we consider the atlas of known exact solutions to Einstein equations, those solutions are known as Kerr-Nut de Sitter or Kerr-Nut anti-de Sitter, or just Kerr-Nut. And indeed, they contain such horizons, if you know how to look for them. So in this way, we can generalize our considerations of this extremal horizon from horizons that have global section to horizons that don't have global section. And we will get a lot of exact conditions. So this is it.
So this horizon is a non-trivial bundle of the sphere.
Yes, in that case,
There are no global.
yeah, and in addition to this, that this is non-global bundle, this null vector field is going transversally to the fiber of the bundle, which means that the orbits are not close; they are infinite. So they have quite chaos, and they don't define well the space of null. So the space of null generators is not well defined. Okay, I have some more slides, but that was it is the case. If there were more questions, if not, I think you can be already sufficiently informed by.
And this group by Maciek and Lucetti do do you know this? Can you follow this proof? Can you say something about it?
Well, I follow in a sense that when they say that all terms drop, then I believe them that all terms drop. I didn't check term by term in the
Because this is what kind of proof? Some topology must enter, no?
It's just algebra. It's just
You know, you reckon it's enter because you integrate over the harmonic function.
yes, but right. So what you have to prove, this non-trivial part is that this left hand side. So we construct psi defined by this. And
This
we-
lemma is also
We know
there are solutions F. There is a solution F such that
But this is the
Right, yeah.
I know that this is another.
But this F must be global. F
Yes.
must be global.
F is global and no.
So in this sense, topology somehow.
Yeah. Okay, yeah.
Here also this compactness and in this group.
And
Yes.
compactness.
Yes, so I didn't mean that compactness doesn't and global theorems don't play a role. I mean that the last step of the group is that you take this
Where and you prove
You
it
use
is
this,
direct.
you use the equation and patiently you check that the terms you obtain really cancel. And that you obtain your errors.
So I think that the first part, existence of F, is more
Yeah, this is a
difficult.
functional.
Yeah, but this is just given for granted by, I mean, it's just given by those people, they speak. For this specific operator.
Yeah, so okay, you say that they looked into old papers by Anderson, Mars, and Simon.
Simon, Walter Simon.
Walter Simon.
No, this is German.
Yeah, because this operator is known as Motz operator.
So why these people did
Okay,
solve the problem?
because they didn't consider this problem. They considered Motz operator, this operator, because it describes the divergence of imaginary
Extremality of mass.
where it is extended in some dimensions, and they have some theory of stability.
Okay, so they were not interested in near horizon.
They were not aware of application of this operator in this stuff.
So it is interesting how Lewandowski and Lucetti found this. Perhaps Lewandowski knew this result by Simon. No?
Oh yes, they are just well. I don't think Dunaisky knew. I think that Lucetti knew this result because this result is. I mean, I also knew about this operator, but
I remember this paper too. Yeah.
but I didn't really remember that. So there is something nice that in this way, given a one form, there exists a unique vector field which is divergence free and which is of this form. So this is just by itself some knowledge.
F is a kind of a gauge. Yeah,
Well, sort of. It's not really. Yeah, but it comes from rescaling imaginary transfers, then this F is going to be scaling. So this even needs some choice.
So this completes proof of uniqueness of extremal care.
Of extremal. It's for the and for time being without Maxwell field, because if we try with Maxwell field, but then it's not simple. This calculation produces more time. So let's work it out. Or maybe come up with a little secret
But for the case with the maximum, yes, the case of the transport, so can you manifest?
Yes, so this is what we check, that if we consider current Newman axis symmetric, then this d phi again is the first form. However, we didn't check this with topological constant. And but it is true, that it's again of the same form. So it seems that this, however, if you do it for the Maxwell Einstein and for Einstein Maxwell case, then instead of lambda, even if you do this in lambda, even if it's lambda equals 0, instead of lambda, you obtain absolute value squared of one of the components of the electromagnetic field. So in a sense, you replace lambda, constant lambda by a function. And then if you repeat this, then you also obtain derivatives of this function, which produce some which are very ugly, and we don't know what to do. But maybe I think it's doable. It might be okay, so if there are more questions,
So maybe let's send the speaker. And other some questions.
Spytaj sieci. Jurek, spytaj ty.
are there questions from Zoom viewers?
Who is on Zoom?
No, I think they are not.
Nikt się nie ujawnił.
Okay, so we already discussed. But
Okay, so